Welcome, folks. Thanks for coming. Happy Wednesday. Today we have Zachary Steyn. Zachary was a Tuckwell Scholar at the Australian National University, where he earned his bachelor's in statistics in 2022 and astrophysics in 2024. Zach is now a second-year PhD student working with Professor Christian Wolff. He's working on continuum reverberation mapping, which is what we're going to hear about today. And his first authored paper was actually accepted just a few months ago on this very topic as well. So we're very excited to hear about this and have him talk about this. Save your questions to the end. And Zach, take it away.
Awesome. Thank you very much. It's really nice to meet everyone here in person, and hello to those online. Yeah, as Meg said, this is a talk about continuum reverberation mapping, which means when we get down to it, I'm going to talk to you about two things. One of them being AGN and the other one being reverb. So first, just so everyone has a clear picture about AGN in their mind, as a quick refresher, you have the supermassive black hole in the center. Around that, you have the X-ray corona, so these relativistic electrons upscattering seed photons from the disk and shining back down on the surrounding region. You have the accretion disk, which is kind of the main powerhouse that we see. You also have the broadliner region, this line emission that's been broadened because of the high virial velocities. And all of that is sort of enclosed by this picture of a dusty torus. If you think you remember other components, don't worry, they're not relevant at all for this talk, so you can forget about those. But yeah, that's the brief AGN update. Now, talking about the more exciting part, the reverb. So one of the things I really want to get across about this is this concept that the physical space can be encoded in a linear response. And I personally find that really easy to interpret with things like sound. So what I've made that hopefully works is just like a basic drum loop that I made in GarageBand. Just sounds normal. Now, I can take that signal and I can convolve it with a linear response function that imparts into the signal the geometry of a space in which it could be played. So for example, if I was to play that drum set in a large hall, compared to the first one, you can hear that it sounds a lot more roomy, versus if I play that in a small bedroom, it sounds a lot more flat. So that's sort of the principle here, that the geometry is encoded in the response. So how does that actually work in a real AGN? So the picture here is that you have the central X-ray corona, and that shines on the surrounding accretion disk. And because this corona is variable, that variable emission, when it is reprocessed by the disk and re-emitted at that local temperature, will follow those same variations, but it'll do so with a time delay. And because you have the inner region being hotter than the outer region, you'll see this response first at lower wavelengths. If we try and measure the time delay between two continuum bands that both probe the disk, we can then use that to estimate what the distance between their emitting regions are. Now, this has been applied quite successfully to very intensive studies of local AGN. So I'm showing an example lag spectra. So that just means the time delay is a function of wavelength from the first AGN storm campaign. And you can see there's a coherent shape in the way that the time delay increases with is that the magnitude of this larger than we'd expect, and it's generally by a factor 3. And this is comparison to the Shkunis-Sunyaev model with some pretty basic assumptions. But does that really mean we have a big issue with our accretion physics? Maybe not. There's a few ways that we could try and explain this. And one of the ways is through having another emitting source contributing to these lags, and that being the broadliner region. So what I've chucked up there on the right is an example model spectra of the emission that would come from the broadliner region that includes the lines and also the continuum series. So that includes the Balmer and the Passion series. And you would expect, if you have two delay signals one from a much closer disk and one from a much further away BLR. But what the average signal you would measure is some weighted combination of the two based on how much of the flux comes from each. And you can see kind of qualitatively on the left there that you get a rise around where the Balmer jump is, and you get another rise around where the Paschen jump is. So this may be a potential explanation. But whether the signatures for this sort of BLR continuum shape crop up in the lag spectra, that's not really universal. Some systems show it more, some show it a lot less. So one of the ways you can try and explore whether this is a population level behavior is to turn to large survey studies. Because it's not really feasible to try and have these really intensive studies for everyone. You have to kind of exchange some of your data quality in order to get this larger sample. And with that comes having slightly less well-constrained lags. So you can see up on the right there is a plot of recovered delays that you measure versus the ones that you expect. And it's kind of on average sort of following that line, but it's a lot noisier than it was before. But again, going back to the benefit of turning to these large sample studies is you get to look at that population level behavior. And pretty much universally at the population level, what people have seen is this sort of size mismatch of how much bigger things are than what we expected is anti-correlated with luminosity. So you should think if you go to luminous enough disks, everything should be all right again. So to try and test that, what we wanted to do is look at some of the most luminous quasars in the sky. So we take a sample of about 10,000 AGN, and you can see here in the comparison distribution with the black surface being just the general SDSS quasars from DR14Q, and the top colored points is our sample. You can see that we're really occupying that sort of luminous edge where we want to study whether this anti-correlation persists. Just for a bit of context as well, I've put an example light curve up. So this is two band data that we have from the NASA Atlas survey. One is the cyan band and one is the orange. And those roughly correspond to G plus R, and then another one being R plus I. So they're very broadband filters. But you can see the stochastic variation that we hope to track across the different bands. And you can also see that when we do this, we don't have regular sampling. So it means it's a little more difficult to try and reinfer what these lags are. For comparison as well, what we have is a very, very large sample, like almost 10,000 AGN. That's almost an order of magnitude than the previous studies. And that means we get some really, really good population level statistics. One of the other things that if you look at the results from previous works is that you'll have sort of a pool of potential candidate objects, and you'll have several hundred light curves that you might be able to search through. But when you do that, you can only constrain robustly a lag for a small fraction of them. It gets a little bit dependent on your data quality and the actual stochastic variability that you observe. Because I suppose if you think about it, if your light curve is just sort of a linear trend, no matter how much I shift them left and right, they're always going to be kind of highly correlated. So you need some sort of stationary point to anchor what your specific delays are. The more the better. But with these previous studies, if they couldn't constrain a lag, they sort of chucked out the rest of the data, and they only looked at the ones they could constrain. We wanted to think, if we were looking at the population level, whether there was a way that we could still use that information to inform on this population behavior, instead of just chucking it away. So what I want to show here is a comparison on a simulated data set. So this simulated data set is calibrated to the real Atlas data, and it's pretty much one-to-one. For every one object that we have one simulated light curve pair. And we're going to test out, in this example, the Javelin algorithm, which is a Gaussian process algorithm that you just feed into an MCMC sampler to derive, among other parameters, but of mostly our interest is the time delay parameter. When you apply this in the original method of where every light curve pair is treated individually, you see a very large scatter of points. And this doesn't really follow the intrinsic distribution of which they were simulated on. If you make a cut so that you're only choosing the significant lags, you end up biasing your distribution. And that's not very helpful if you're trying to look for signatures of whether or not your lags are larger than you expect. What you can do is you can make a quality cut. So for instance, based on how correlated your two bands are, or how variable they are, with the expectation being if they're more strongly correlated or they're more variable, it should be easier to measure a lag. And you do see an improvement there. You see that the delays now sort of follow the distribution a lot better than you expect, but this is also a cut that selects the top 1%. So again, we're chucking out quite a lot of the data. And while this worked for a simulated data set, the real AGN picture is a lot more complicated. So for instance, both correlation and variability are correlated with color. So if you make a cut on one, you end up making a cut by the other. And as I'm going to show a little bit later, color has an effect on the magnitude of the lags that you measure. So while it's useful in a simulated data set, if you want to look at the population level, you're already imposing a selection effect just from looking at data quality. So if that's out, we move on to just binning the posteriors. So taking away individual estimates, summing them up and seeing what the average distribution looks like. You can see that there's no bias and it follows the trend reasonably well, but the uncertainties are much too large. If you want to look at any small scale behavior or small scale structure, you're going to miss it. Finally, if instead what you do is you bin your sample discretely and you infer a joint parameter, so this is stacking your likelihood functions during your MC-MC sampler. So when you're deciding whether or not you should accept or reject a proposal, you're taking into account the full sort of nearby population. When you do this, not only do you get a much better constraint on the lags that you see, and you can see it follows the intrinsic simulation quite well, the expected answer, but the uncertainty is much, much lower. So you can start to investigate these small scale structures. There are a few points there you might notice have quite large error bars, and they're kind of faded out a little bit more. But that's a bit of a known issue with MC-MC sampling in a Gaussian process like this when you're trying to look at lags. Because of this irregular sampling that we have, you end up getting quite a coarse likelihood distribution. And if your MC-MC sampler can't navigate between the different peaks quite well, it can end up getting stuck between them. So the distributions that I've sort of grayed out a little bit and made them a little more faint, those are ones that have multimodal posteriors, so ones that got stuck. So what do we recover when we apply this method to the real data, the real AGN light curves? So again, as I mentioned, we're discretely binning our population. So what I've done is 10 bins in rest frame wavelength, and within each of those 10 bins, 5 bins in log luminosity. Here I've translated this luminosity into a unit of an expected time delay just for easier comparison with the expectation. But if you kind of think about it this way, the luminosity sets the scale of the disk. If you want to increase the luminosity, you need a larger accretion disk, and it kind of goes with the area approximately. And the wavelength sets on what position of the disk you're probing. So these two things are kind of what's controlling our lag. When we find that when you actually are controlling for these redshift effects, if you look at any one of these panels individually, you see qualitatively it sort of scales as we expect. And because we're only letting in each bin it depend on luminosity, this is the appropriate luminosity scaling, at least qualitatively. So this means that in our data, when we control for redshift, we don't find this anti-correlation as opposed to all the previous population level studies. But why is that? Why did the other previous population level studies find an anti-correlation and we don't? So if you take, for instance, what I'm about to do here is the average amplitude ratio in each one of these bins, and you show how it changes with wavelength, you get this non-monotonic trend right here, where on average, if you go to shorter wavelengths, you would predict delays to be more in line with what you would expect. Now, if you were looking at taking one of these other population level studies, for example, because they don't simultaneously control for redshift, which is something that we're able to do because of our large population, you're kind of averaging out this effect. If you take two really widely separated filters, you get a nice smooth trend with wavelength. And because you have a flux limited sample, if you want to go to a more luminous one, you're inherently going to a shorter wavelength as well. One of the other things that these studies do is if they use multiple bands, they average between them. So you kind of miss this non-monotonicity that we see here, which we're really sensitive to probing because the Atlas bands are really, really close together. In fact, they're overlapping. Now, this non-monotonic behavior, where you can see this rise and then a dip and then a rise again, is a signature that some of the emission that we're probing is not coming from the accretion disk, that instead it might be coming from the broadline region. So the plot on the right there is showing, for several model examples, a lag spectra that you would expect from a broadline region contamination. So you can see if we take two filters and we put them on the right and we look at the time delay between them and we go through Redshift and we drag these filters through, then you would qualitatively get the plot on the left. That the minima sort of around the Balmer jump when the cyan band is sitting on top of in the Balmer continuum and the orange band is sitting just on the other side. That's actually where you get the minima in our plot on the left. So this is just kind of showing that it's not so easy to disentangle the two signals, that you will get contributions from both, which is somewhat bad news for people who are solely fans of the accretion disk, but it might open up the interesting possibility to study both at the same time. Again, using the same method, what we can do is bin by other parameters. So this is now that same plot I showed before, but now we also control for Eddington ratio. You can see as you go through the plots, the high Eddington ratio points, which are the blue circles, more often than not sit on top of the equivalent low Eddington ratio source, which is the orange triangles. So we see here that higher Eddington ratio sources have longer lags. We can also play a similar game with the ion ratios. So that's the equivalent width of the ion complex to the relevant low ionization line. So for the high redshift bins, that's been panels 1 to 6, that is the UV ion relative to the magnesium 2. And for the low redshift bins, which are panels 7 through 10, that's the optical ion to the H beta. Now, you see a very similar trend here that the high ion ratios also have longer lags. Now, does this mean that this is a signature that the broadline region changes or exhibiting a change in the continuum of days? Maybe. So these two parameters are themselves correlated. If you are familiar with the eigenvector 1 space, the idea that there's this fundamental plane on which quasar spectra vary, you'll find that the Eddington ratio and the ion ratio are two correlated quantities. And it becomes very difficult with this binning method to try and separate them out at the same time. We don't quite have the sample statistics and the signal to try and control for both. So at this stage, it's still a bit unsure which one of these parameters is driving it. They both could infer changes in the broadline region, or they both could be tracing an Eddington ratio effect with disk structure. But to find out more, you also have to look at the spectra, which is one of the things I'm going to flag here is a future item of work. So going on to other parameters that we can explore by, this photometric color. So because we have fixed observed frame filters, the color between them is a function of redshift. There's line emissions coming in and out of the filters. But once we control for that, we see we get a nice distribution. It's approximately Gaussian, and then you see a red tail. The idea here being that you have this core distribution that may be an intrinsic quasar color distribution, or maybe it's an intrinsic reddening distribution, but we're making sure to cut out all the things that definitely look dust reddened. Because here the idea being if there's a significant dust extinction component, then you're going to underestimate the luminosity, and therefore you're going to underestimate the true size of the accretion disk. And then, of course, you're going to have a size problem. So when we take this core distribution, we break it down by color. You might be able to see that it gets a little bit noisier here. That's because we're now splitting by three bins within each panel, 3 color bins. So we're losing some of these sample statistics, but I thought it was really important to show that this is an ordered effect. Sort of on average, what you see is that you get a redder color having the longer lags and the bluer color having shorter lags. Now, this might potentially open up the very interesting prospect of using quasar time delays to measure dust extinction. And you can do this without an absolute calibration. If you have just measured from the data what the blue quasars are doing, you can find what the red delay is, find out how much larger it is than you expect, and translate that directly into how much of the luminosity you're underestimating. But there's a few other things that might be going on. For example, we already have signatures that the broadline region is contributing to our lags with that non-monotonic dependence with wavelength. And the continuum of the Balmer and Paschen series are both redder than the intrinsic accretion disk. So what you would also okay, I think okay, I will start sharing again. Sorry about that. Okay, share. Is it coming back through on the Zoom now? Maybe soon. Awesome, fantastic. Sorry about that. But yeah, we can go and we can basically play this game exploring as many different parameters that we can get our hands on, and see how the delay behavior changes. So next on our list is carbon-4 emission line profiles. So this idea that you will get an outflow if you can measure a blue shift in your carbon-4 line. We wanted to see whether these outflowing winds have an effect on our disk reprocessing. This is where it gets a lot more complicated, though. If I focus on these two bins that I've highlighted now, you might notice that the cyan filter, which is our leading band, directly is contaminated by the carbon-4 emission. So this makes it very hard to disentangle the two effects, what the carbon-4 emission line profile is doing and what the lag is doing, because they're inherently probing a similar time domain structure. Now, because we have an anti-correlation between our blue shift, the strength of our outflow, and the equivalent width, how much of that emission is contributing to our band, you would expect a smaller contribution from the carbon-4 emission line in the quasars that have higher blue shifts, because the BLR structure is coming from a further away place in the AGN. It's more distant radially. You would expect a larger average radius in the cyan band if the carbon-4 emission there is stronger. Therefore, when you measure the difference between the average cyan band radius and the average orange band radius, it's the quasars, or at least it looks like here, the quasars with the stronger blue shift, and therefore the smaller equivalent width, and the shorter the smaller carbon-4 radius have a larger difference. And you can see that this sort of behavior flips as soon as you get to the one redshift band that we have that's not directly contaminated. So panel number 3. Now, it's really hard to tell whether this is a robust effect because we only have that one extra panel. So that's 5 bins for comparison to say that there is this flip in the dichotomy of which one is the longer lags. But it's really hard to generate this flip in behavior without something that's localized in wavelength. Now, the thing here then is if we weren't contaminated by the carbon-4 bands, for having smaller blue shift, have longer lags is kind of incongruent and doesn't really match with our eigenvector 1 interpretation, because these higher Eddington ratio sources also should have higher carbon-4 blue shifts. So does this mean that this is a distinct and different trend? Maybe. So the other thing to consider here is that we're making our cut there on the red line. So that's at a blue shift of 1800 kilometers. 1800 kilometers a second. If we take an example from another study, which compares the fraction of quasars that show broad absorption line troughs we're actually getting the peak of this distribution in our low carbon 4 blue shift wind. Because we've removed all of the broad emission line trough quasars to try and more accurately infer the carbon 4 line properties. We're technically not probing this population, but our spectra are taken like 15 years before our photometric survey started. And broad absorption line troughs are a transient feature. So what potentially could be happening as well is our low blue shift bin, our low carbon 4 blue shift bin, which is the orange triangles, has the longer lag because it's had more broad absorption line transients appear since the spectra were taken. Now, again, because these are transient features and it's temporally separated from our photometric data, it's quite hard to get at this property. But we do make a comparison based on the historic values for whether or not a quasar has broad absorption line troughs in its carbon 4 emission or not. This again becomes a much more difficult comparison because the fraction of quasars that have these broad absorption troughs gets a lot smaller. But it's not inconsistent with the interpretation that broad absorption lines make your lags longer. And that's been seen in other much more intensive studies of AGN, where you do have that time resolution between what the absorption troughs are doing and what the lags are doing as well. It kind of points to, if you want to sort of probe this time varying structure, you at least need to have some sort of idea about what the other properties in your broad emission line region are doing. It's sort of, I don't know, as a bit of a tangent, I guess, if you want to do future studies like this and you want to sort of zero in on what this effect is, you can't really do it without having spectra taken around the same time. If lags are a time varying phenomenon based on the properties that the AGN are currently experiencing, you need to know both in order to inform your lags better. To sort of bring this to a summary, I want to leave this with a few key points. The first one being, if you want to infer the population level parameters, it's much better to do so jointly. So instead of treating all of your quasars as individual, treat them as part of the same population that should be having some sort of dependency on its lags. You want to use the information that you get from all the different ones to infer what the population level statistics are doing. Now, I think this style of analysis becomes quite complementary to people who fit a lot more physical models, because the benefit of doing this population level analysis is that you get to probe things in a more model agnostic way. You wouldn't be able to get the signal to do so in individual quasars, but if you leverage the fact that they should have this sort of same physical behavior, you can probe that more deeply and get to the systematics of those issues. Another thing I want to impress upon more is that there is this reasonably distinct signature that the broadline region is contributing to continuum delays. It's not just the signal from the disk. If you want to understand one or the other, you need to account for the fact that the other one's there. Now, again, sort of going back to trying to do this in a model agnostic way, like if you just care about the disk, your disk inference is biased by however much you don't understand how the broadline region is contaminating. If what you're interested in is the broadline region, that's biased by how limited your disk interpretation is. So it's important to try and take into account that both signals are there when you're looking at these systems. And so the last point I want to stress is the fact that these delays change as a function of AGN parameters. This sort of offers up a new way to not just as a geometric probe, but to probe the same physical mechanisms that go on in AGN, sorry. When you take a spectra, you're looking at sort of like this zeroth order moment, how bright things are as a function of wavelength. This is now taking other moments. You're now looking at sort of like a radial average of this emission. And understanding how both changes, understanding that it must be the same region that produces both, helps you dive deeper into what the true physics of AGN are. Thank you very much for listening, and please let me know if you have any questions.
Or if you had a question first, you do that. Okay, so if, say we, in that red plot, if we didn't have any contamination from the BLR, would we expect those blue points to follow the tau SSD? If our model assumptions were correct.
If your model of accretion disk physics was perfect and what the delays would be, you would expect it to follow that black line, yeah. If it was true that all accretion disks which happen to be a factor 3 larger than you expected, all the points should be on the red line. If it's some more complex model, you'd expect it to be some way amount between them, but you'd expect it if it was all disk signal to be happening in a monotonic way, because it's really difficult to take some sort of structure that has a gradient in temperature and make this non-monotonic behavior in wavelength. You'd need more of the longer wavelength emission at this particular region to be also coming from a shorter region, which doesn't quite work if you're having hotter on the middle, smoothly going out, cooler on the outside.
Yeah. And is there any way to map, this is very convoluted, but is there some way to map that disruption in the temperature gradient using this contamination and the lags that we measured? You know, like go to a different wavelength instead of cyan and orange, different wavelength band, and see how this contamination pattern changes and map that to like, okay, the BLR is contaminating or contributing in a different way here.
Yes. Yeah. So that's kind of what we do when we go through different redshifts. But sort of part of the difficulty there is that our filters are super broad. So this probably isn't the data set that you want to use if you want to make sort of like a variable emission spectra of the BLR. There are some people who do it with very narrow band filters, and you can choose them really precisely to not coincide with the broad line emission lines, and you can try and probe more directly what the accretion disk is doing. And in the studies that do that, particularly when they look at shorter wavelengths, they generally find lags that are much more consistent with the sizes of accretion disks that we expect. And the other thing I kind of didn't mention is that this thing is more of like a differential spectra, lag spectra. We have the differences between two filters. Because they're not the differences to some common filter, we're kind of missing this overall amplitude. So while this is very good for probing discontinuities in the lag spectra, it's much less able to try and tell you whether there is an absolute problem with the normalization. So I'm not sure if I would be able to comment on whether the time delays underneath the broadline signal are consistent with the model or not, but that's certainly something I'd want to look into later. Thanks.
I think I missed a bit your sample selection. So if I understand correctly, in order to make this type of studies, you need to select sources where you're sure that you have a standard disk and where you're sure that you can see the broadline region. So type 1 AGN is a standard disk, right?
Type 1 AGN, we do go up to Eddington ratios around 1. And there you might see some departure from what you'd expect a standard disk to be, maybe moving away from this sort of slim disk picture more towards a slim disk picture. That might be potentially why we get a dependence on Eddington ratio, that as you go to these higher Eddington ratios, you're probing a different physical structure in the disk, but there are a lot of potential reasons that Eddington ratio could be correlated with the magnitude of our delays. And because we have evidence that the delays are not just the disk signal, and they also have the BLR, it means that it could be a correlation between BLR properties and Eddington ratio rather than a change in disk structure. And one way to separate that out would be to go back and to look at the spectra, which is what I plan on doing next.
Because you also have a correlation with this delay with the luminosity, or anti-correlation, you said.
So the previous population.
Luminosity in X.
The plot before did show X-ray, but it happens as well with the UV because they're quite tightly coupled.
It's kind of anti-correlating with the disk or disk size.
So that anti-correlation was about how much larger you measure things to be as a ratio to what you'd expect. So it was in that the previous population studies were looking at, when they looked at more or faint AGN, they found a larger mismatch between their observations and the expectation. And when they went to more luminous AGN, they found less of a deviation. But we found that when we controlled for redshift, so that's going back to this plot here, you no longer get that anti-correlation. When you control for the redshift, because you're in a flux limited sample, so now we're now specifying that these objects have to be probing the same wavelength, the delays now probe on the same sort of gradient that you'd expect from the model. So you kind of lose this anti-correlation. It was more, yeah, because previous studies weren't controlling for the fact that the wavelength was also changing when they go to more luminous AGN.
But you think that there may be also a contribution on the fact that you may have different geometry in the disk, or not some of your sources may not have a standard disk.
No. And hopefully these continuum delays would be an awesome way to try and probe how that structure changes. Because there is already kind of a deviation from what you'd expect just looking at the spectra, that often when you go to higher Eddington ratio sources, there's more of a deviation in the ultraviolet. So this could be a nice independent check. But yeah, thank you for the question.
Any other questions? I have none. We're excited about Rubin. Rubin may vastly increase your sample size, fingers crossed, and maybe in the deep drilling fields we'll have a good enough cadence to probe some awesome physics, these accretion disks, very luminous quasars. You mentioned that you would ideally get spectroscopic data coupled to the photometric data in similar timeframes, right? What do you think that the largest gap is between like a spectrum being taken or spectrums being taken and like the photometric observations to be able to like do this work? So I know that there are a ton of spectroscopic surveys following Rubin, but there are going to be delays between the photometric and spectroscopic observations.
So I think to do this sort of population level analysis, and I'm not particularly advocating for doing it in this discrete binning way in the future, because that was, I suppose, more of a back of the envelope, let's just chunk it up and see how it goes. You can fit more complex Bayesian models, but the spectra in this instance are what determine how similar an AGN is. So how close you need the spectra to your data depends on how rapidly the properties that you deem to classify AGN as similar change. So for instance, thinking about the broad absorption line troughs and wanting to probe that, how quickly they disappear and reappear in systems and how much those properties change. As sort of the times. I mean, of course, you'd want as closely matched as you can, but as long as it's still approximate that these are similar systems, I think it's okay.
Thank you.
Thanks.
Let's thank Zach again.